And Arun, it's over to you. You're muted, Arun.
Yeah, sure. Thank you, Ram, and good morning, everybody, and welcome to the day 2 of the ACM eEnergy 2021 conference. This is session 3, Analytics and Control in Smart Buildings. And we have 3 full papers in this session, including one which is nominated for the Best Paper Award, which will be presented as the last talk in this session. So the first paper is titled Energon, a data acquisition system for portable building analytics. The presenter is Fang. A very brief bio. Fang is a first-year PhD candidate from the computing department of the Hong Kong Polytechnic University. His research lies at the intersection of smart buildings, energy conservation systems, and data mining. And most recently, his work is focused on the management and organization of building information. With that, I'll hand it over to you, Fang. Thank you. Fang, please, can you share your presentation, and it's over to you.
Okay. Can you see me?
Yes, we can see you.
Okay? Yeah.
Your screen is not shared your presentation. We cannot see, but we can see you. Yeah, this is fine. Please go ahead. Thank you.
Hello, everyone. My name is Fang. I'm a PhD candidate from the Department of Computing, the Hong Kong Polytechnic University. The paper I will present today is titled Energon, a data acquisition system for portable building analytics. This is a full paper. Building analytics, it is using data to develop machine learning-based methods for the operation and control of building systems. They have proven to be effective in providing control and fault prognosis of building systems, reducing energy footprint, improving the comfort of occupants. There is an increasing number of data-driven building analytics in literature. To develop building analytics, not only expertise about building analytics, but also building domain knowledge is required, especially in the data access stage. In more detail, the knowledge about what algorithm fits, what control points are available in the targeted systems, and how to access these points in the specific configuration of each individual building are needed to be made clear. Currently, developing and deploying analytics still requires tremendous manual effort on a per building basis because of the varying system details in each building. This greatly impedes the adoption of building analytics. Luckily, there are recent efforts dedicated to standardizing resource and information organization to reduce the required domain knowledge in buildings and to facilitating access to building data, such as BRIC. In BRIC, the building resources and the relationships are defined as RDF triples. Thus, SparkQL, a graph-based query language, can be used for locating data required by building analytics, as long as the developers of building analytics has a clear understanding of all the entities in the building and the relationship among them. However, even if for the same analytic, customized SparkQL scripts are required in different buildings. Nevertheless, portable building analytics should be deployed across different buildings without requiring major changes to the implementation. So in the data access stage, can we extract data for building analytics in a building agnostic way? In this paper, we present Energon, a data acquisition system for portable building analytics, which can extract building data and agnostic to the building specifics. Before we proceed to the detailed system design, we first need to understand what building specific knowledge impedes data acquisition for building analytics. Here we conclude 3 types of auxiliary knowledge. Let's illustrate them with the example of building integrated control. It is the joint control of the lighting system and the blind system for indoor visual comfort. to train a machine learning model for this building analytics, the involved data from both lighting system and the blind system are required. So the first is the spatial auxiliary knowledge. The structure of building subsystems often varies from building to building. For example, the lighting system in building A only contains lamp, the set point of which controls the luminous level. While in building B, the set point of both the lamp and the ballast control the luminous level. The second is temporal auxiliary knowledge. A building subsystem may have a seasonal usage pattern. For example, lighting 2 is detached from a room to save energy because of ample light in the summer. The last is the contextual auxiliary knowledge. Building subsystem may be used in different contexts. For example, lighting and blind systems are used in the context of rooms in building A, but in zones in building B. Obviously, to customize two spatial scripts for these two buildings, these three kinds of building-dependent auxiliary knowledge is required because of the different building specifics. As the three types of building-dependent auxiliary knowledge are needed to be evaded when retrieving data, we would need to have a proper abstraction of the building data required by analytics and to build upon it, which is akin to how an Android program is developed regardless of the underlying specifications of the phone. To create such an abstraction, we examine some major categories of building analytics as listed in this table. We categorize building data into two logic partitions, named subsystem and functionality. For instance, the building integrated control analytics need the data involved in lighting, blind, and weather in view of subsystem, and the solar radiance, solar angle, and the set point in view of functionality. Thus, we abstract the data according to the subsystem and the functionality involved, and then develop corresponding data extraction operations on this category using declarative queries. More specifically, building analytics are built upon building subsystems. The data associated with functionality are also required. To reach the data of different subsystems, spatial, temporal, and contextual auxiliary knowledge is needed. So we also develop standard query operations which help to hide different types of auxiliary knowledge. For example, select, from, where, union, intersect, and so on. So based on these two logic partitions and query operations, we present Energon query language. Here we give an example of Energon query. The select, from, and where clauses specify ontology traversal, bounding, and selection, respectively. Specifically, the ontology from building PU is selected and bounded to object B, from which the lighting and blind system with set points related nodes in B are traversed. The filter clause further specifies the filtering conditions for ontology and data selection. Now we give the architecture of Energon system. Energon has three parts: Energon query language, based on spatial for the data acquisition process of building analytics; Energon query engine for Energon query language interpretation and execution; Energon ontology index developed for system performance optimization; and the database stores the building data and the building ontology. The main part is the Energon query engine, which presents a standardized execution procedure for building analytics. There are three steps. First, the declarative query processing module processes the query and generates a query execution plan. Second, the building independent ontology extraction module extracts the sub-ontology out of the building ontology based on user queries. Finally, the data extraction module takes the sub-ontology for data extraction via standard programming interfaces. In the declarative query processing module, the query parser passes the query string into a set of tokens called a query syntax tree. During the normalization step, the predicates are normalized to the conjective normal form. Then the query transformer converts the normalized tree into a query execution plan, represented as ordered internal functions calls accessing both the ontology and the time series databases for the building. The execution plan obtains a subset of building data that will further be used in the data modeling. In the building independent ontology extraction module, there are two substeps. The ontology segment extraction module takes an existing building ontology and extracts a set of ontology segments corresponding to the two categories, subsystem and functionality. The algebra-assisted ontology composition module takes the extracted set of ontology segments and performs operations specified in the query to derive a sub-ontology. Let's go back to the example. In the case of extracting partition data for building integrated control, the subsystem expression selects the ontology segment of lighting system in building B. More specifically, the involved node of lighting system in building B can be selected. Then the functionality expressions select the luminous set point functionality ontology segments in building B. Once again, the involved node of luminous set point in building B can be selected. Thus, the intersection of lighting and the set point finds the luminous set point in the lighting system. So the entire expression selects this data point, these data nodes. Energon allows operations on top of ontology segments to compose the final sub-ontology by Energon algebra defined like this. That is, upon the ontology relations G1 to GR, the following two types of clauses, well and filter, denoted by sigma with S function over conditions phi1 to phi m, and tau with F function over conditions omega 1 to omega n, are performed to determine the pending ontology. Then the ontology extraction pi with P function with projected attributes P1 to Pk is performed to compose a building sub-ontology. Based on Energon algebra, we define four fundamental operations to conduct an ontology composition, which are union, intersection, difference, and join. Since union, intersection, and difference are easy to understand, let's focus on join, using the example of building integrated control again. We introduce join operator to merge the subsystems with relationships. In Energon algebra, join operator is a binary operator that can only be performed on two subsystems, and thus its results can be regarded as a further subsystem. Building integrated control needs the data from the lighting system and the corresponding blind system. The algebra can be expressed as lighting join blind. To extract the sub-ontology, the query engine traverses the RDF triples recursively to search the paths between the pieces of equipment in lighting system, lighting 1 and lighting 2, and the equipment in blind system, blind 1 and blind 2. As shown, there are two paths were searched by the query engine. It is the lighting 1 to blind 1, as well as lighting 2 to blind 1. Thus, all the sensors from these three equipment are extracted. It's easy to verify that Energon algebra has three algebra equivalence laws: commutative, associative, and distributive. This ensures consistency when developers write Energon queries in different ways. For example, to extract the luminous data and set point data from the lighting system in a building, the algebra can be expressed as lighting intersects luminous unites lighting intersects set point. With the distribution property, the algebra can also be expressed as lighting intersects left bracket, luminous unites set point right bracket. Energon stores the RDF triples constituting a building ontology graph in a ontology storage structure. This heavily influences the execution of an Energon query, especially the ontology extraction process. A common ontology storage structure is to store the entire ontology as RDF triples like figure A. This can incur significant execution overhead for processing Energon queries. Specifically, the subsystems of Energon query have a hierarchical structure. For example, lamp and ballast are children of lighting. Yet a storage in RDF triples does nothing to maintain such a hierarchical structure. Represent the Energon ontology index structure to maintain the hierarchical structure of a building ontology into an adjacency list, like figure B. This allows for immediate positioning of substructure of an entity. We maintain a list of each subsystem as building analytics as based on subsystems. This Energon ontology indexing structure basically sacrifices a memory space of ON to substitute a time complexity of O square of N. Then we qualitatively and quantitatively evaluate Energon by implementing 4 real-world analytics. We compare the development effort required when using Energon to that for a state-of-the-art system, MOTA, in terms of program length and program development time. We see a drastic reduction in the total number of lines of code for all 4 analytics. This is attributed to the effective abstraction of ontology extraction and data extraction, which can be done with standard select from where queries expressions in Energon, whereas with MOTA, building specific spatial queries need to be written with an understanding of the specifics of the building, a key difficulty during the development of the analytics. We also see that with Energon QR, developers spend less time on implementing the analytics. This is partially because for each analytics in Energon QR, the developer does not need to understand the details of every new building ontology. We then evaluate our indexing storage optimization. We found that our indexing storage schema substantially reduces the ontology extraction time, and that the average execution time among the 4 analytics is reduced by more than 1,000 times for all 4 mentioned building analytics. This is attributed to the effective indexing mechanism, which avoids time-consuming traversals with RDF triples in this stage. In addition, we studied 2 factors that influence the time consumption of ontology extraction. The first one is query constituents, and the second one is building ontology size. The execution mainly consists of 3 parts: subsystem extraction, functionality extraction, and the operator performing. We find that no part dominates the whole process. We also note that even for the same analytics, ontology extraction time varies across buildings because the scale of their ontology differs. Figure B shows the ontology extraction time in 2 buildings, while the ontology size of building 1 is 5 times over that of building 2. However, we see that the time consumption in building 1 only increased by about 50%. Our proposed subsystem segment index stores both directly and indirectly connected equipment. And therefore, even when the building scale increases dramatically, the traversal time only grows at a moderate pace. Here are the conclusions. First, we present a new abstraction of building resources so that developers do not need to have building-specific knowledge when developing building analytics. Thus, the development of analytics can be simplified. Secondly, we present the design and the implementation of Energon to materialize the abstraction. We develop a declarative query language to evade building dependent and analytics in relevant knowledge. we developed a query engine for automatically extracting data by traversing a building ontology that widely exists in buildings. We further developed an indexing structure to optimize query execution time. Thirdly, we developed 4 types of building analytics through Energon, and we qualitatively shown that the development process becomes simpler when using Energon. Finally, we quantitatively evaluate Energon with regard to program length and development time. We evaluate our optimization schemas designed for execution time in Energon. Here are some references. Thank you, and I would be happy to answer questions.
Great.
So,
thank you, Fang. Thank you. Questions, please, from the audience? Yeah, Herman, please go ahead.
So how different can the buildings be for your approach to work? Is there, or what's the degree of similarity with regards, let's say, to energy must be there for the scheme to work?
May I beg your pardon?
Well, if you look at a building, let's say, of a university, a campus building, and then you look to a factory and you look to a private home, they're completely different in the way they're operated. And so, yeah, would it work in all these settings? And what is the limitations, perhaps?
Oh, okay. Let me see. And I think the key is the abstraction, the 2 abstraction. It is the 2 logic partitions we proposed in this work, named functionality and subsystem. I think in industry buildings or housework or residential buildings, there are all these 2 kind of abstractions in the buildings, and the key is how to use these abstractions.
Is there any limitation, would you say, or does it always work if you use the abstraction correctly?
Yeah, I think the limitation is how to determine the terms that express the subsystem and the functionality. As you see in my example, lighting and blind. So how to define lighting, how to define blind, I think is the limitation. Actually we are on the way to solve this problem. Yeah.
Okay. All right. Thanks.
Thank
you. Any other questions? Yes, please, Dan, go ahead. You had a comment to the previous question.
I just want to follow up Herman's question. It's a very, very good question. The problem we are solving, the developer, they need to know what data they need to develop the model. Okay. For example, for a chiller, they want to develop a machine learning model. They need to know what kind of data they need. Our abstraction just remove how to reach the data, because different chillers in different buildings, they have different sensing structures. Okay, and reaching this data differs from building to building. And our abstraction, by abstracting into a sub-function, and then what data, for example, temperature or return water temperature or return water flow, it is much easier. So yeah, Energon is superior in this sense. Yeah.
Okay. So I have another question, somewhat related. So from my experience looking at different building management systems, all of these systems tend to store the data that they log in different kinds of databases or different kinds of file formats Some may be standardized, some may be very local to that specific BMS vendor. Now, in order to extract this data and for Energon to work in these different types of BMS systems, what is the real input that you require? And how are you kind of overcoming the problem in the industry side of different vendors having different ways to tag the data and store the data as well?
Oh, okay. So probably I give 2 cents, and then probably Fang can add to it. So it's like a driver. So a building, okay, if you want to follow Energon's abstraction, then you can develop your own driver. Currently, we request in our experiment, we request the building to connect to brick, which is a kind of a layer of standardization. Yes. So after you connect to brick, then you can directly be accessed. Your data can be directly accessed by Energon. But if you don't want to connect to brick, you develop another driver, okay, following the Energon's abstraction, and then you can connect to connect in. Yeah, that makes sense.
Right. So your underlying abstraction that you rely on has to be followed by any a layer below that, which actually stores the data, whatever, right? Okay.
Yes.
And in terms of the impact with the industry, are there any insights, Dan, about potentially standardizing this or looking at if BMS vendors are able to, use these kinds of abstractions for Energon's purposes?
Okay. Yeah. How industry will adopt, right, Energon? So this is a very interesting question. I can only say that number one, we do save the developers time. Yeah, they only need to worry about the subsystem and the machine learning model that they want to develop. They don't need to worry about how to find the data, how to in each specific subsystem. So this is number one. Number two is that they can, well, this is why we tie with brick. Okay, so as long as you follow brick, that's easier. Another one is that we try to go to companies and governments and do some push. Yeah.
Okay.
Yeah, there are some ongoing efforts in this direction, but take some time to show.
Yes, of course. Okay, thank you very much. If there are no more questions or if there are any coming up, please can I request you all to use the Slack channel and we can continue that discussion there. So maybe we can just thank the speaker again, Fang, and also move on to the next talk.